and therefore they have somewhat different temperatures, somewhat different energies, right? So in general, the flux on the electron before the last scattering is not isotropic, okay? That's similar to what we see in CMB anisotropy today, but this electron, the guy that upscatters the photons for the last time, also sees some anisotropy around, right? Now, if we consider photons coming from, all kinds of directions, then the photon that upscatters the electron comes to us polarized, even if the initial flux of photons in this direction was unpolarized. And the reason is that the photon essentially doesn't want to change its polarization when it scatters, okay? So the cross-section, the sigma Thomson d omega, is proportional. Let me write down the proportionality coefficient. This is sigma total over 8 pi times the modulus of the product of incoming polarization and outgoing polarization of incoming photon. This prime will always denote the incoming photon. So this photon comes from direction n prime with momentum k prime, okay, which are aligned, of course, and it has a certain polarization epsilon prime, okay. So what does this mean? This means that if photon comes from, say, this direction here, okay, say, and upscatters at right angle to us, then if this photon has this polarization, epsilon prime, then it will have some non-vanishing cross-section to scatter, whereas the photon that comes from with the polarization this one, epsilon prime, then this photon will have zero cross-section if it's right angle, right? Because its polarization is directed towards us, right? And therefore, the polarization vector remains in the scattering plane, so this guy will not scatter at all, right? If photon comes in some, from some direction there, then of course this is no longer true, because this polarization here, epsilon prime, and polarization to us, which is this one, so this is a scattering plane, right? Photon coming here will have polarization in this direction, and their scalar product will not be zero any longer, okay? And the photons that come directly to us and scatter at very small angles, they will all have the same cross-section, right, irrespectively of polarization. Okay, that's the story. So if, for example, we have a warm region here, so we have warm region here, and we ask, and here is the electron which scatters photons for the last time, we may ask, will we see polarization coming, or photons coming to us, right? And the answer is yes, because suppose that this is also in perpendicular plane, for simplicity. So we have more photons coming from here, right? They will all come to us with polarization epsilon prime, epsilon in this direction, perpendicular to the direction of photon propagation to us. They will all have the same polarization here, and there will be more photons since this is a warm region. Even if the photons here are unpolarized initially, they will scatter off to us. They will all get polarization in this direction, right? And therefore, we will see polarized light, polarized cosmic microwave background coming to us. If we have such a situation, it will be polarized this way. Okay, this will be the polarization vector of photons. Will have dominantly this polarization vector. Okay. Well, all this discussion tells you that polarization is linear. So, linear polarization. Okay? There is no circular polarization generated. It's always linear. That's one thing. Second thing is that effect is small. Why? Because photons have finite distance to travel before their scattering in here and the last scattering, the scattering before the last one and the last one. Okay, they travel finite distance. And clearly, what is this distance? This distance is kind of average free path of a photon before the very last scattering. Okay? What does it mean? In other words, we have finite thickness in time and in space of the last scattering surface, right? So the free path of photon before the last scattering is of order of this thickness of the last scattering surface, right? So the photon travel this distance between the consecutive scattering, the last one being the very last scattering, okay? And this is small. This is small compared to the wavelength of perturbations we are up to, okay? Our typical scales of perturbations, typical wavelength of perturbations, lambda perturbations, is roughly, we're talking about multiples of order of 100, maybe 1,000. Roughly, it's proportional to 1 over eta r, right? Remember, this is the time, conformal time of the last scattering epoch, and the momenta of perturbations, lambda is proportional to eta r. The moment of perturbations of, say, multiple of 100 is just a order of this eta r, inverse of eta r. The wavelength is a order of eta r. Okay? So typically there will be a suppression factor k times eta r, delta eta r. Why? Because we need an isotropy before the last scattering. If we have waves of momenta k, waves of perturbations, k is the momentum of perturbation. Right? So if our momentum of perturbation is small, meaning that the wavelength of perturbation is large, then this means that the temperature varies very little on the scale delta eta r, okay? And therefore, the effect will be suppressed by this factor, Okay, the polarization effect will be suppressed by this factor. Okay, for infinitely long perturbations, there will be no effect whatsoever, simply because temperature for photons coming from here and temperature for photons coming from there will be the same. My perturbation is independent of space. So there will be suppression by this factor here. Okay. Now, to estimate the magnitude of this suppression, we need to estimate the magnitude of this suppression. Well, for that we have to understand how the density of free electrons falls off in time, right? Because what is the thickness of the last scattering surface? The density of why is it of finite thickness? Because the density of electrons, free electrons, falls down at finite speed, and therefore it's not immediate that they were numerous electrons and then zero electrons. No, it falls with finite speed. So once the number of electrons changes by a factor of roughly 2, for example, then the scattering probability changes by the same factor, and therefore the the typical thickness of the last scattering surface is determined by the rate at which the density of free electrons decreases with time. Okay, the typical time scale of the decrease of the number density of free electrons in expanding universe. That's what we are about. So we need to understand how the number density of free electrons. The only process here is Thomson scattering, the scattering of photons of free electrons. Right. So we need to know the number density of free electrons. So how does it behave as a function of time? Well, it behaves as a function of temperature, the number of free electrons, as some slowly varying function of temperature. Doesn't matter exactly what it is. And then there is an exponential factor, which is minus delta H over 2 for temperatures. Okay, where delta H is the binding energy of electron in hydrogen atom. 13.6 electron volts. It's binding energy of electron in the hydrogen atom. Now, then you must be surprised. You must be surprised because normally, of course, the number of free electrons is equal to the number of free protons, right, by electron neutrality, i.e. the number of atoms that didn't combine into the number of nuclei that didn't combine into hydrogen atoms, right? The number of protons that did not combine into hydrogen atoms. And you must be surprised that this number falls off like this, like it to the binding energy over 4 temperatures. Normally, you would expect in equilibrium, in thermal equilibrium, you would expect that the number of free protons divided by the number of hydrogen atoms towards the end of recombination. We're interested in the situation towards the end of recombination when almost all protons combined into hydrogen, and there are few electrons, not very many electrons. You would expect it to be to behave like e to the minus delta H over temperature, right? The ratio of this is just a Boltzmann factor, right? The okay, the proton plus electron has bigger energy as compared to hydrogen atom just by the binding energy. So you would expect this. This is true. In thermal equilibrium, this is correct. However, recombination turns out to be in equilibrium process. That's a particular feature of recombination in the real universe, that the expansion of the, even though the expansion of the universe is very slow, its characteristic time is the lifetime of the universe, 400,000 years. Nevertheless, it turns out that there are so few protons and electrons in plasma that the recombination is not equilibrium process. You have to understand that. And the physics is actually quite nice. Let me spend maybe 5 minutes by discussing it. The point is that what do we have? What system do we have? We have hydrogen. Hydrogen has continuum, which means free electrons and free protons. Then there is 1s level. And superficially, you would think that what can happen is that electron and proton would combine and immediately get down to the ground state, 1s. Okay, so there is the process of direct recombination with a photon emitted at this energy, or somewhat above this energy, 13.6 electron volt. Right? But these are harmless photons. This is a harmless process. The point is that these photons, there are very, very few photons of this energy at temperatures of interest. And temperature of interest is 0.26 electron volts. Okay, that's the temperature of recombination, of fast scattering. So at this temperature, there are very, very few photons of this high energy. So these photons will pretty soon meet hydrogen atom again and disintegrate it. Okay? There will be an inverse process of disintegration of hydrogen to proton and electron induced by these photons, these highly energetic photons. Okay? So all in all, this process doesn't reduce the number of free electrons and doesn't increase the number of atoms. You gain one atom and then you lose one. Okay? So what happens is that actually there is a set of levels which are 2s and 2p levels. Okay? So what happens is that there is a recombination down here, and these are in thermal equilibrium all the time. There is enough photons of energy. Remember that the binding energy of 2s and 2p is a quarter of binding energy of the ground state. Okay, so there are quite a few photons of this lower energy, of a quarter of the binding energy of hydrogen in plasma. So these processes are in thermal equilibrium. These guys get formed and destroyed simply by the photons in the heat bath. They are destroyed by photons in the heat bath. Okay? And then there is a slow process of leakage from these two down to 1s. 2s goes to 1s plus 2 photons, and these 2 photons cannot do anything. They don't have enough energy. Each of them doesn't have enough energy to excite the ground state. And also, the Lyman alpha photon, which comes from 2p, Lyman alpha photon, these guys actually do not excite, I mean some of them at least, do not excite the hydrogen atom. They rather get redshifted because of the expansion of the universe and can no longer excite the hydrogen 1s level up to 2p level. This is a very narrow line. It moves quickly enough from the region where its energy is sufficient to excite 1s level. And so these two processes work together, and these are relatively slow. So what happens is that there is this equilibrium, thermal equilibrium between these parts, these excited levels and continuum, and there is no thermal equilibrium in the lower part of this plot. Okay, so the number of electrons is free electrons is effectively determined by the equilibrium between the continuum and the excited states, 2s and 2p mostly, and therefore the number of free electrons decreases as the binding energy of the 2s or 2p level divided by temperature. Okay, that's how it goes. So in fact, if you look at some textbooks, they miss this point. This point is not very well known for particle theorists, at least. So be careful when reading some books on cosmology written by particle theorists, particle physicists. Okay? So anyhow, this is how the things work, and therefore the number of electrons, and that's actually very important for the, numerically very important for the polarization, because this behavior means that the characteristic temperature is such that delta H over 4 temperature delta T over T, that's the scale at which the number density decreases by a factor of E. Okay, this is the delta T change in temperature. This determines for you the characteristic width of the thickness of the last scattering surface. So you say that it must be a 4-1, and now remember we are at matter-dominated epoch, so temperature goes like inverse of the scale factor, and the scale factor is proportional to eta squared. Therefore, this gives us delta H over 2 temperature delta eta over eta at recombination or at last scattering for the 1. So delta eta at recombination over eta recombination. This is the typical suppression factor for multiples of 100. This will be for 2 temperature over delta H. Okay, and this is indeed a small number, given that the temperature is 0.26 electron volts, delta is 13.6 electron volts. So altogether, you get this suppression factor, which is of 0.04. Okay, this gives you the magnitude of suppression at multiples of interest of the polarization of cosmic microwave background. Okay, a few percent. Okay, and of course the fact that there is this factor 4 is important, because otherwise you will have 4 times larger, 4 times smaller width of 4 times, smaller width of the last scattering surface. Okay, so, right. So one immediately understands the magnitude of the polarization, namely, if we think about the momenta of 1 over eta r, then the degree of polarization will be something like k times delta eta r times delta t over t. That's the rough estimate for the magnitude we have, right? So this will give us something like a few percent, or 0.04, times delta t over t. This will be a degree of polarization, or if we multiply this by temperature to cast everything in units of Kelvin, so T times the degree of polarization is going to be roughly a few percent of delta T. Okay? Delta T is on the order of a few times 10 to the minus 5, so altogether this is going to be something like 10 to the minus 6 Kelvin, which gives microkelvin. So in these units we expect the polarization at microkelvin level, or in other words, degree of polarization on the order of 10 to the minus 6. So only one of the of million photons will be polarized, roughly speaking. That's a tiny effect, and that's why it's very difficult to search for it. Right? And you need very precise data to figure out that the cosmic microwave background is polarized at the level of 10 to the minus 6. Okay. Right. Now, there is one more effect. I was talking here about polarization that is generated at recombination epoch. That's not the whole story, because cosmic medium is ionized also at late epoch. That goes under the name of secondary ionization or reionization. At z of order 10, relatively recently, because of formation of the first stars and their explosions, etc., there will be massive release of energy, which in the end ionizes, as people believe, ionizes the hydrogen again. Okay? And therefore, just like in the case of polarization generated at recombination epoch, there will be also polarization generated at this reionization epoch and later, because photons that come to electrons, which again are free at this epoch, photons coming from different directions, they again have different temperatures, as we know, right? This is just the CMB anisotropy, temperature anisotropy we measure. And again, their scattering produces polarization. But this has to do with very low multiples. L, roughly eta reionization, eta 0 to eta reionization. Okay? And smaller. Why? Because these electrons are very far away from the emission region of relic photons from last scattering surface. So they collect everything that comes from the last scattering surface, okay, And so you have to average over the light cone, which was almost the same light cone as we have today, up to the fact that this eta reionization was by a factor of 3 smaller than we have it today. So this can only give rise to very low multiples, or you average over large regions of the last scattering sphere, and therefore you get low multiples only. Roughly this is 3, so the secondary ionization gives rise to polarization at angular scales of order, at multiples of order of maybe 3, 4, 5, at maximum 10. Okay? So that's another source of polarization. Let me just tell you that to make contact with what's written in experimental papers, if you assume that there was instantaneous reionization, then of course you can relate this redshift at which instantaneous and complete. Complete means all hydrogen atoms were ionized again. Then there is one-to-one correspondence between that reionization and what's called how is it called? Optical depth, right, exactly. Optical depth due to this reionization, and this tells you how much photons have been actually scattered off by electrons at reionization epoch and data. Optical depth. So there is one-to-one correspondence because once you know this Z, then you know the density of electrons. We know how much hydrogen we have now, so we know how much hydrogen we had today. This is just 1 plus Z cube density, and so number of free electrons is known, and then you can figure out what is the optical depth. So typically this reionization is parameterized by this single parameter, which turns out observationally to be of the order of 0.089 according to Planck. Okay, and this is consistent to what WMAP measures, and this corresponds to reionization of order 10 to 10.5 plus or minus 1.2. The redshift. That's actually fortunate that we didn't have complete, very optically deep, optically thick reionization epoch. If it occurred somewhat earlier, then this optical depth could be of order 1, and then we would not see the signal from the recombination epoch. All these photons will be scattered by electrons at reionization and later, but this shows us that only about 1 photon out of 10 is scattered at reionization. So in that case, suppression factor here for the reionization is again on the order of 1%, but now it's because this optical depth is over 1%. Okay, so the effect is small, but for different reasons. For reason that only 1 out of 10, 1 out of 10 photons will be scattered. It will be on the order of a few percent at best. Okay? Right, so there are two effects the effect is all the same, but there are two sources. One source is at recombination, and it works at essentially all multipoles, although it is suppressed at small multipoles, which correspond to small k. Okay, but still it's there at all multipoles, whereas this effect works for low multiples only, large angular scales only. Okay. And one more thing, again, I have to be rather qualitative, otherwise every of these issues will take lectures, several lectures, maybe one or two lectures, but there is one more effect which is rather complicated, and it has to do with lensing. The photons that travel through the universe are lensed by structures in the universe. They change their directionality. Because of the change of this directionality, the polarization pattern changes, and therefore there is an effect that that distorts the polarization pattern on the sky. It's actually quite important. Right. Okay. So let's proceed with formalism. How do you qualitatively describe this polarization pattern? Suppose you measure it. How do you describe it? Well, the way to describe it is to say that if I look at photons coming to me, then these photons have electric field, which is transfers to the line of sight. So A is 1 and 2, and these correspond to coordinates on the celestial sphere. Okay, and E is the normal to my line of sight, so it's tangential to celestial sphere. I have electric field. Okay, and then I construct polarization tensor PAB, which is tensor on the celestial sphere, right? Which is traced as part of EA, EB minus traced as part, 1/2 of delta AB E squared, EC, divided by the overall intensity E squared. Okay, where brackets here mean averaging over the oscillations of my electric field. Okay, my electric field oscillates. It's linear polarization. It oscillates, and I average over oscillations. So I introduced it in such a way that its trace is equal to 0, and if my signal radio waves, if they are not polarized, then this PAB is 0. Okay, if there is no polarization singled out, then PAB is 0. Okay, that's polarization tensor. The eigenvalues of it are, of course, one positive, one negative, with definite, equal to each other in modulus, since its trace is 0. So the degree of polarization is square root of the positive eigenvalue, lambda 1, 2. The eigenvalues are plus and minus lambda. So this is degree of polarization, and one can visualize the polarization by considering the polarization vector PA right, which is also normal to the sphere, which is which normal to the line of sight, which is the eigenvector of this polarization tensor with largest eigenvalue. Okay, which means that the light is polarized along this vector. Okay. So that's how people make and visualize the polarization pattern. And let me show one example here. This is produced by WMAP. See, all these vectors here are polarization vectors. Okay, so this is how the cosmic microwave background is polarized on large scales. Okay, and these are galactic regions, red ones, which you have to subtract. Okay, so there is some polarization pattern in the cosmic microwave background. Probably the signal, I don't know. The signal here is probably too weak to decide. All right, so, but this is not the most convenient way. By the way, to make contact with what Planck shows, suppose you have a spot in the sky, say cold spot, surrounded by hot sphere. Okay. Then at angular scale, at distance here, okay, I'm looking at my sky here, and so this is angle, right? So this angle, delta theta, is delta eta r over eta 0. Delta eta r is the distance, typical distance, which photon travel from this cold spot to the scattering point where the scatter of electron the last time moved to us. And this is distance here, coordinate distance is delta eta r, whereas the angular scale is delta eta r to our present eta, okay, which should be quite a bit smaller than an angle. So you expect here following picture. My photons coming from the cold spot are less numerous, okay, and therefore you expect polarization of this sort, right? There is a lack of photons polarized in normal direction to this line. There is lack of photons polarized along this direction. Okay, if this were warm spot, then there will be excess of photons polarized in the normal direction. If it's cold, then there is a lack of photons polarized in normal direction to this line. So what you expect is that you have polarization pattern like this, okay? Whereas these guys are hot, so further out you expect polarization pattern like that, okay? Coming from the hot part, further out, you are expecting this kind of polarization. So polarization pattern is like this, here and here, here, here. Okay? And indeed, what Planck was proudly showing is this. So here is temperature profile. This is cold spot. It says that it's a combination of real data up here. And this is indistinguishable from it is the simulation. Okay. So anyhow, this is a cold spot here, surrounded by warm sphere, and here is this is temperature, and this is polarization pattern. Because of this cold spot, you get here vectors along the radius vector on a sphere, or on this little part of the sphere, and here you have polarization vectors normal to the radial vector. Okay, just this picture that you expect. Okay. I wonder why they, with such a nice, data, they didn't yet show their polarization data in full. Okay, but this is not the most convenient way to characterize your polarization pattern. Convenient way to be similar turns out to be similar to the analysis of temperature of the cosmic microwave background. Okay, you have your polarization pattern, and you would like to expand in spherical harmonics. Okay. Well, this is tensor, so we have to expand tensor, symmetric tensor, in terms of spherical harmonics. This is actually very well known, probably not for everybody in this audience, what are tensor spherical harmonics. Who knows what is tensor spherical harmonic? You didn't learn quantum mechanics properly. All right, so let me introduce them. The idea, suppose I'm not on a sphere, suppose I'm on a plane. I'm considering a small part of a sphere which is similar to a plane, right? So I have a tensor on a plane. I have a tensor on a plane, PAB, okay? And I want to expand it in Fourier, okay? I expand it in Fourier, then I have that it depends on momentum. Let me call it Q, to confuse you even more. Okay? So how would you expand this PAB in Fourier mode? Where do you put your indices A and B? Well, there is an obvious candidate. An obvious candidate is QA, QB. This is symmetric, okay? QB. But, this is 4x4 matrix. So there must be more than one combination. So let's call it P1. Okay, now it's a scalar. But I can also, so there are two vectors, right? There is one vector QA and another vector epsilon AB QB, right? Where epsilon is antisymmetric tensor, okay? So I have two natural basis vectors, and I can expand my tensor in these natural basis vectors. This is one. Second is epsilon AC QC times QB, right? This is essentially 1 component, QQ component. If I call this E1 and I call this E2 basis vectors, then this is 1 component. This is 1 2 component, but I have to add epsilon B C Q C QA to 1. They are equal to each other. Okay, P2, and then I have 2 component, which is epsilon AC epsilon BD QC QD P3. Okay, right. This is symmetric tensor, and I expand it in natural coordinate system, which is related to the Fourier, to the momentum you introduce once you do Fourier decomposition. But I also have to impose the relation that trace of it, PAA, is 0. I'm dealing with traceless tensor. This is automatically traceless. okay, because this is 1-2 component. But for that, I need that P1 plus P3 equals 0, okay? So in this plain example, I have two components, two scalar components. One is QA, QB minus epsilon A, C epsilon A, BD, QC, QD. Let me call it PE. And the second one is the P2, epsilon AC, QC, epsilon, QA, QB plus epsilon BC, QC, QA, PB. So I have two independent scalar components for symmetric traceless 2x2 tensor, which are naturally expanded in the coordinate frame related to your momentum. Okay? So this is called E mode, this is called B mode. Why notation? Notation comes from the observation that if I take the divergence of this tensor, QA, PAB, then obviously it's going to be first one, Q squared, QB, PE. Okay, that gives me 0. Here, this term gives me 0 when I multiply by QA. And here, this term gives me Q squared, QA, PB. Oh, sorry. Epsilon BC, QC, PB. Right? This comes when I multiply this term here by Q. Okay? So the divergence of the tensor is vector, and this vector is decomposed into longitudinal part and transverse part. Okay? And that's why the notation E is kind of similarity to electric field. Longitudinal one, whereas this one is kind of curl, right? So it's similar to magnetic field. It's vague, but that's just to give you an idea of why the notation is this. Anyhow, this is now generalized to sphere. We're not interested in a plane, but we are interested in a sphere. And generalization is pretty obvious. You can either write this way, or you can cast this term. This is QA, QB minus its trace, right, essentially. So basically this is usually, okay, let me forget about the various normalizations. So this will give me QA, QB minus 1/2 of Q squared delta AB. This is the same thing, PE, and PB remains the same. So anyway, this is generalized to sphere by writing that PAB is the following, is 1/2 nabla A nabla B plus nabla B nabla A minus gamma AB Laplacian PE. Okay, I get back to coordinate space. Here I was in momentum space, here I'm in coordinate space, never mind. And the second term is 1/2 of epsilon AC nabla B nabla C plus epsilon BC nabla A nabla C PB. Okay? Where nabla is covariant derivative on a sphere, Laplacian is also Laplacian on a sphere, gamma AB is metric on a sphere. Okay? That's the definition of parity even and parity odd. Sorry, E and B modes on a sphere. Okay? And then you can decompose the scalars into spherical harmonics, in spherical harmonics, right? Just like we did for temperature anisotropy. Okay. Now, so the final formulae are horrible, but who cares? So you introduce the spherical harmonics of E-type, Lm AB. It carries these two indices. Essentially, you write here decomposition in terms of spherical harmonics, and what this operator does, it makes a tensor harmonic out of scalar harmonic, right? So it's essentially this. You need also some normalization so that they're normalized to L minus 2 factorial, L plus 2 factorial, normalization factor, and this nabla A, nabla B, minus 1/2 of delta AB Laplacian of conventional spherical harmonic Lm, right? And this is E-type, and B-type Lm AB is the same similar factor within a factor of 2 to L plus 2 factorial, and here I have epsilon AC nabla B nabla C plus epsilon BC nabla A nabla C YLM. So that's the definition of spherical harmonics, and your PAB, of, depending on n, can be decomposed into A Lm E Y Lm E of n plus, same with B, A Lm B Y Lm AB AB B of n. Okay, that's the decomposition into spherical harmonics of a symmetric tensor of the second rank. Okay, so now you know what the spherical harmonics are, right? It's spherical. It's a tensorial analog of spherical harmonics in the scalar case. Okay, and these factors here are introduced in such a way that these guys are orthogonal and normalized functions in the space of tensors. Okay. So what you do then, once you have your pattern of polarization on the sky, measured on the sky, you take this pattern and decompose into spherical harmonics like this. Okay, and the inverse is of course obvious. It's the same story as with conventional spherical harmonics. ALME equals to integral PAB YLMAB E dn. Okay, you integrate over the whole sky with this tensor spherical harmonic. You extract, the same for B. You extract a E and a B LM, and then make the all kinds of averages. By average, again, meaning summing over, averaging over m, over this second quantum number. Okay? And this way you arrive at what's called CL. Now for us, there is an important difference between E and B modes. Seen both here and here. This is parity, right? The first one is parity even, okay? There is no epsilon symbol anywhere. It's parity even. Well, modulo the fact that YLM, okay, anyhow, this is parity even. This is a scalar function, P is a scalar function, so it's a parity even thing, okay? Whereas the second one is parity odd. This one is parity odd. For example, if you if you take your potentials P, again, let me go to plane. Well, the story is the same for sphere. Let me consider a small part of the sphere. Let's suppose that P, E, and B depend only on the radius on the plane, right? Rho is the radius on the plane. Then, what's this pattern here? We can, straightforwardly calculate all these derivatives, okay, and then figure out what the eigenvectors are. Where do they direct? Okay. So this is spherically symmetric thing. Now for E mode, okay, depending on the sign, the positive eigenvalue has eigenvector either this way, normal to the radius vector, or this way. Just as we saw, as we see still in this picture. Okay? This is E mode. Depending on the sign here, either vector normal to radius vector or vector along radius vector has the largest eigenvalue. Okay? There is no directionality of this vector. I don't write this. I should have possibly written like that. But there is no directionality. The polarization, the electric vector oscillates back and forth, so there's no difference between this vector and the vector. So there is no way to assign an arrow to this vector, in other words. There are no arrows here as well. Now for B mode, you have a different story. I invite you to calculate on a plane what this thing means. Figure out what the eigenvectors are. And the eigenvectors are like this. I always have trouble to write. So they are inclined to the radius vector by 45 degrees. Etc. Okay, that's how it looks. Okay. 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 That's the pattern you would have for spherically symmetric, for rotationally symmetric potential PB, if you just do this differentiation and figure out what the pattern is. Okay, it's obviously this thing here. If you just rotate you make a parity transformation. In other words, you rotate this fashion by 180 degrees, it will stay the same, right? This way, this thing as well. Here is different. If you rotate by 190 degrees, this vector will come here, right? This vector will become that one. Why don't I use this chalk here? This vector will become that one. This vector will become this one. So you will have B mode with of opposite sign. Okay. So this guy is parity symmetric, parity even. This guy is parity odd. It changes sign under parity. Okay. And that's a big difference from the viewpoint of observational viewpoint and significance of this E and B mode. It's a very big difference. Why? Well, because scalar perturbations give only oops. The contribution. Oh, forgot one of my sheets. Okay. Anyway, vector perturbations. Scalar perturbations give rise only to the E mode. Let me maybe. Well, it's kind of obvious, right? Since they are scalars, there is no way to construct epsilon symbol out of them, right? You only can differentiate, which means they remain scalars. So there is no way of getting parity odd thing. In other words, let me write down one formula for you. Formula is this. Suppose I have again photons that come from direction k. Let's see, yeah, they come from direction k prime and upscatter to me, and I observe them at a certain position on the sky, which is characterized by vector n, right? So I have vector n there, and to the very last scattering, photon come from direction n prime. Okay? Then what's going to be the polarization tensor? Well, I can write the electric field, electric vector of photon that comes to me, the final photon that comes to me, as the electric vector E prime of the photon that is going to scatter, that hasn't scattered yet, minus n E prime. That's the same formula as I wrote in the very beginning. That tells me that the cross section for different polarizations. This is, by the way, the classical formula of scattering of a photon or electromagnetic wave on a dipole. Okay, coefficient here, which is the total scattering cross section. This is how the electric fields are related. Okay. In particular, this E is normal to the vector n of the motion of the photon after scattering. Okay, so this is n. This is okay. Now, the point is that from here I can calculate what is the average of AE, AB, right? Since I know, suppose I have an unpolarized influx. For unpolarized influx, I have E prime, E, A, I, J.
This is delta ij model of the fact that it should be orthogonal to momentum k prime. It's delta I minus n prime I n prime j, right? Where n prime is the directionality of a photon before scattering. And from here, I can straightforwardly calculate what the polarization tensor is. And polarization tensor turns out to be PAB that I measure for photons that come from the direction k prime. It's equal to half delta AB minus n 1 minus n prime n squared, I think minus EA n prime EB n prime, where EA are two basis vectors. In a given coordinate frame, I have two basis vectors labeled by index A. So components of, say, a vector is the scalar product of this vector with this EA, will be the eighth component of a vector, etc. So this is going to be the polarization tensor for photons that come from direction n prime, scatter to me, and come to me with direction a direction n. Okay. The point to make here is that basically what you have to do is to take this polarization tensor, multiply it by the delta t over t in the direction n prime, okay, minus n prime rather, integrate over all scattering positions of photons. They could be further or closer to this electron here. I have to integrate along a certain region here, but that's kind of technicality. And I should integrate over all n primes, all directionalities of photon coming to this electron, scattering to me at in the direction n, and this will be my polarization tensor I observe, right? But the whole point here is that this operation here is a scalar operation, or rather, it's a parity even operation, I should say. This operation here is parity even operation. If you change all your directionalities by to minus, then you get the same thing. Okay. So whether or not I have parity odd PAB, meaning B mode, depends on the properties of this factor here. If it is parity even, then you create only parity even modes. If it has parity odd component, then I can create also B modes. I will create necessarily also B modes. All right. Now, for scalar modes, I know what delta t are, what delta t is, right? We figured that out in our last lecture, but now this delta t is not what I see. This delta t is temperature that this electron sees, right? The temperature in the direction n prime of this electron here, depending on the directionality from this guy, this electron. I almost said him. Okay, so this electron sees temperature and isotropy of photons coming from all directions here, and for him, this electron, delta t over t is again the same story as before. It's a Sachs-Wolfert term, 1/4 delta gamma plus phi plus v times n prime. V is the velocity, Doppler term, plus integral phi prime minus psi prime d eta. From the next to last scattering, eta RR, to the position of this electron, okay, to the time of this electron, time of last scattering. So the point again here is that this is a scalar thing, right? Sorry, this V is nk, for mode of a given momentum k, for mode of perturbation of a given momentum k, this is nk times the velocity potential, if you remember. Therefore, this is a scalar product of two n's. N that corresponds to momentum k, and n that corresponds to the directionality of a photon, right? There are numerous directions here. This is the direction of perturbation, and this is the direction of photon that comes to scatter last time. Okay? So this is, again, scalar quantity. That's the whole point. There is no way you can generate epsilon symbols here. There's no way you can generate terms that change sign upon parity transformation. Okay? So scalar perturbations generate only modes, and we understand why. Now, how about tensor perturbations? Tensor perturbations, remember, delta t over t is integral from the next to last scattering to the last scattering of hij n I hij d eta. Okay, let me not write down the prime, because prime will mean denote the photon, n I j. Yeah. If I have two scalars, you mean nonlinear effects? Well, nonlinear effects can produce B mode for you as well. That's true. And essentially, that's what happens due to lensing. And think of, distributions, meta distribution as another scalar, right? So you have one scalar that produces E mode, and then meta distribution, another scalar, makes B mode out of it. It's a nonlinear effect, right? Yeah, at nonlinear level, you can produce B mode. Now here, let's see. Let's do a simple calculation here. What is it? Okay, suppose I have a mode. Now this is K. This is the gravity wave. So n prime is the photon directionality. K is directionality of gravity wave. Okay, so here is K. And let me choose the coordinate frame in such a way that the K goes this. It goes along the third axis. So my E1 and E2. So this is this is E2, this is E1. These are transverse vectors. Okay, so this is my coordinate frame, 3 transverse vectors. And remember, hij, one of the hij cross, is actually E1I, E2j plus I2j. Okay? Right? This is the polarization tensor times. This is polarization tensor h cross. This is the amplitude of gravity wave, and this is its polarization tensor. I forget about square root of 2 here. Right? Let's see what does this mean. Suppose my photon travels through this gravitational wave, okay, and suppose that this photon and prime has in this coordinate frame has usual coordinates, sine theta, cos phi, sine theta, sine phi. Okay? Put primes here. Okay? So that the vector of this photon in the background flowing through this wave, okay? So then delta t over t is proportional to, well, easy. This times that, right? Sine squared theta prime cosine phi sine phi prime. Oops, we've got parity odd thing. Because if you change phi by minus phi, you have change in the sign. So we've got parity odd delta t over t, and since all the rest is parity even, I'm going to generate B mode. Okay? Right, so that's how things go. I do generate B mode by gravitational waves. Unfortunately, I was not able to. I can do am I filmed? Okay, I'll try to give you a pretty weird example. No, I don't care. If it's wrong, it's wrong. But I tried to give a simple example. You see, we had the nice example of what happens if we have this nice example here. Now, I tried to do the same, simple geometrical example with gravity wave. And I'm not sure I did that correct. So but anyhow, suppose I have a gravitational wave that travels in this direction, normal to the blackboard. Okay? So here is E1, here is E2. Okay? Now, suppose this is a blob, meaning that it's a wave packet in normal direction. Okay, it's not infinitely large gravitational wave. It's contained in this region here. So it travels that direction. Momentum goes that direction, and the amplitudes is not zero, only within this region here. Okay, similar to hot spot, right, or cold spot. Now, suppose I'm looking at photons. Now, the photons that travel around without touching this this region, suppose they are isotropic. But now let's see what's going on to happen. Let's now take the H, it's more clear, Ij equal to E1I E1J minus E2I E2J. This is another polarization of gravitational wave. Okay? Simple to draw pictures. So photon that travel this way, this is K prime of photon, right? its polarization tensor, non-trivial part, is directed here. And we are watching this from this, this is the momentum of gravity wave coincides with our line of sight. So this guy has sorry, what I'm saying. So again, I have Hij plus times Nij prime, okay? That's what I'm going to look at. So if the photon travels this direction, then this is E1. Then it becomes warmer because this guy adds to temperature, right? This term here, K prime is, this one is along E1, so this guy adds temperature. So photon comes here and scatters off this electron, and it's warmer than on average, right? So altogether, you're going to get polarization like this here, okay? Now, photon going this direction is cooler because of the second term. It's along E2. So its polarization vector will be this in the end, right? There will be lack of photons normally polarized normal to the radius vector. So my polarization will be this, and at 45 degrees I will have 0, right? These two terms will cancel each other if my n prime is at 45 degrees. Okay, so here I have 0. Okay, so here I have this kind of behavior. Okay, these photons are cooler, these photons are warmer than an average. Okay, so I'm getting at rather weird pattern. Sorry, etc. Okay, same down here. Okay, and obviously, even though it is symmetric under this parity transformation, right? It's not symmetric if you make parity transformation against this line. Okay, you rotate around this line, you get completely different picture. Okay. So this is a mixture, I would think, of E and B modes. So that's kind of geometrical thing. You see, you don't get parity even the simplest case when you have this kind of gravitational wave. You don't get parity even pattern. Your pattern is not parity even if you make the transformation of this sort. Okay, the parity transformation with this line as a reflection line. So even geometrically, even this, but this is the simplest I could imagine, the simplest geometrical picture I could imagine. Maybe I didn't have enough imagination, but that's the simplest geometrical picture I can see, and tells you that things are not as simple as in the case of scalar perturbations. So anyhow, film again. The B modes are produced by gravity waves and also E modes, whereas scalar perturbations produce only E modes. Okay, so I'm about to finish. Now, what is the source of suppression in the case of gravitational waves? Well, there is again suppression, but now by the fact that I have H prime in the expression H dH over d eta, Hij and I and j integrated over the photon path from the next to last scattering to the last scattering, right? That's the contribution to the temperature that enters in the end into polarization, and this is a small number, okay? This is K. For waves, gravitational waves, which are subhorizon. For superhorizon modes, this is 0. So you do expect suppression at low momenta, both in the case of scalar perturbations and in the case of gravity waves, for different reasons. For scalar perturbations, it's because the okay, anyway, I told you about that. So you expect suppression in the amplitude as k in the square, in the correlation functions, or CLs, you expect suppression k squared or L squared, right? Now, final word is that you have, in the case of scalar perturbations, you have two things. You have AELM, right? This is the expansion coefficients for E mode. And you have EALM, let me call it T. This is expansion coefficient in spherical harmonics of temperature fluctuation, right? We called them A in our previous lecture. Let me add superscript T, meaning that it has to do with temperature fluctuations. Now, both of them has, in the case of scalar perturbations, adiabatic mode, they have the same origin, right? They're all coming from, they're all proportional to zeta. Our initial perturbation that, the primordial perturbation that evolves as we discussed, and in the end produces both temperature fluctuation we see and polarization we observe. So no wonder, not only you have ALM E, ALM E equal to CLEE, right? But you also have cross correlator. Since both of them are proportional to one and the same Gaussian random field, you expect also cross correlator with the same property. E, A, L, M, T. Again, they must be delta LL prime, delta MM prime, because of spherical symmetry of my initial perturbations, CLTE. So you've got to have cross correlation, and it's there. That's the first thing that has been clearly measured. Here it is. This is the WMAP data, and this is temperature fluctuation, and this is cross correlation between T and E, between temperature and E mode of polarization. Okay. This part here, as promised, has to do with secondary ionization, and this is the way to estimate, one of the ways to estimate the optical depth here. And you see it's substantial at L of a few. And then there is a well-defined cross correlation. You see it's there. Okay. By the way, it's not quite visible, but if I take this maximum here, it corresponds to the place where velocity is the largest. Okay, and this is true for polarization. What's important, gives the dominant contribution at relatively low multipoles, is velocity of the fluid. Why? Because velocity by itself is already anisotropic, right? Even if you have, even even in the case you don't have high momentum, still velocity has some directionality. It's proportional to its directionality is given by k, by the directionality nk, by the directionality of a polarization of a mode of perturbation, right? So velocity is already has a direction. It's not enough to have just homogeneous flow. Clear? If I have an electron here, if I have a homogeneous flow of my medium, then my photons coming from here will be warm, whereas photons coming from there will be cool, right? Cooler than on average, because of the Doppler effect. And if you have, steady homogeneous flow, then these two effects cancel each other, right? These two effects are equal to each other, but opposite sign. So in polarization, this guy will introduce for me polarization of this sort, but this will have lack of photons polarized this way. So what you need actually is v velocity, which depends on x, on coordinates. So it varies. So that velocity here is, say, bigger than the velocity there. Okay? If the velocity here is bigger than the velocity here, then this will be cooler, but not so. But there will be no compensation between the two. Okay, the Doppler shift of these cooler photons will be lower than in modulus than the Doppler shift of these warmer photons. So the first effect is proportional to gradient divj. The leading order effect will be this, and this gives me one momentum k. Okay, so there is a suppression of k eta r, delta eta r, in the amplitude squared in the moment in the CLs. Okay, so that's going to be the major effect. Whereas if you have temperature, if you have say Sachs-Wolf effect, then there is no directionality in it, so you need two derivatives. So you need delta I, delta J of, say, phi plus 1/4 of delta gamma. And this will introduce for me extra suppression, k delta eta r squared. So if we are talking about not very high momenta, then the Doppler effect is dominant. And that explains why this correlation here is strong when we are on the slope here, similarly here. All right, so let me show one more picture. This is the expectations for contributions of scalar perturbations and tensor perturbations, okay? This is in logarithmic scale, okay? This is E mode, okay? And as I told you, the E mode itself is going to be in the microkelvin range. So this is square of microkelvin. This is 1 microkelvin square. It's a little bit less than 1 microkelvin. Here it's about 1 microkelvin. Now this term here, this part here comes from recombination. This part here comes from the secondary ionization. It's substantial at low multiples. In fact, the optical depth here is twice larger than real one to show the effect. So in fact, this effect is kind of down here. So this is due to secondary ionization. This is due to the recombination epoch here. This is E mode. This is cross correlation. Okay. And as I told you, the larger effect is due to velocity, and velocity is off phase with the main Sachs-Wolf effect contributing to temperature anisotropy. So that's more or less visible here, right? This maximum is at the point where velocity is large. And velocity has opposite phase to the, it oscillates as sine, whereas Sachs-Wolfe oscillates as cosine. Okay? Now this is lensing. This is bad news because B mode that's generated by lensing is substantial already at, you know, rather moderate values of L. And here is gravity wave contribution at unrealistically large value of R, of tensor to scalar ratio. So there is E mode, there is B mode. They both come from secondary ionization here and recombination epoch there. Now, here, as we know, the effect of gravitational waves dies away simply because the gravity waves themselves die away, right? We know that at high momentum, gravitational waves by recombination are suppressed since they decrease after crossing the horizon in, they decreased by recombination, and therefore this goes down. The contribution of gravitational waves goes down. Okay, so the only hope is to observe this part, right? And for larger missions, for missions that will cover the entire celestial sphere, this is a hope as well, because it's not very small effect over the entire celestial sphere. You measure, you might observe B mode of polarization with low multiples. BICEP 2 worked somewhere out here. Somewhere out here. At from 30 to 150. Here. So that's basically it. That's to summarize, B mode is very interesting, as its observation will show that there are gravitational waves or tensor perturbations generated at very early epoch, and the only realistic way to generate them is inflation. So measuring B mode of polarization will tell us that there was inflation, but until we have seen it, you will also be able to doubt the picture of inflationary beginning of the universe. Okay, thanks.